So in general, we do not go from a lag length to confidence level, right? We go from a confidence level to an interval length. So given 90% confidence interval, for example, how may we find the lag length be so that our interval would be right with a 95% probability? Well, again, it's the same thing. It's the same thing. The only difference is that now you are working with a t-distribution, not a uniform distribution. Okay? So we know what's the t-distribution, or eventually you will use software to help you. It's also the case that given any value t, you know how to calculate this. You know what's the probability for a t random variable with degree of freedom n-1 to be less than the given value. Okay? If you need a plot, that means you have a t-distribution and you want to find some left tail probability, because you are asking what's the probability for your capital T to be less than or equal to a specific amount. Okay? When your degree of freedom is 6, you can find the T value to be negative 2.447, so that this probability, this left tail probability is 2.5%. Okay? Then obviously the corresponding right tail probability would also be 2.5%. The graph is ugly, but I hope you will know what I am doing. The left tail probability and the right tail probability must be the same. Okay? So you're going to somewhat apply this particular t value to use that value to do your interval length. Okay? So with this formula, let's see. I know in general, if capital T is less than or equal to small t, then capital T is just this, right? X bar minus mu divided by s over square root of n. So I can change switch the terms and show that this is just that. This is just the probability for mu to be greater than or equal to x bar minus t times s over square root of n. So what's that? That's the probability for my capital X, for my s, to give me a value that is so small. That is so small. So now it's very clear how to get an interval, how to get the lag length. You have this, right? This is your lower bound. And what's this? This is also your lower bound. You are asking what's the probability for this particular thing to be so small, And then what you are doing is to say my lower bound B is this value. Okay? So my lag length can be calculated according to this formula. As long as I have T, as long as I have S, as long as I have N, I can plug in all of them to get this particular thing. Okay? And I get 100 and around 130 to be the lag length of my interval, my 95% interval. So the desired interval would be centered at 960, or centered at the sample mean, with this lag length. If I do that, I can claim that with a 95% confidence interval, I can say my mu is within this region. Okay, that's how I use the t-distribution. So it's almost the same. It's just that the distribution becomes different. Okay, so let's compare the two different ways. One with the population variance, the other one does not. If sigma is known, then things are easier. Given given x bar, given n, and given our desired error rate, we construct the confidence interval in the following steps. First, we realize that x bar is normal. with these parameters. So that means if I define another random variable called z, according to this formula, z would just be standard normal, according to our understanding about standardization of normal distributions. Okay, and then we only need 4 steps. First, calculate the multiplier or the standard error, which is sigma over square root of n. And then calculate a critical value z star so that your standard normal distribution is so small, so that the left tail probability is alpha over 2. Okay, and then once you find your leg length, everything is done. Okay, your leg length should be used here and here, and it's just the product of the critical z star and the multiplier standard error, which is sigma over square root of n. If sigma is unknown, now you need small s in your calculation, in your estimation. First, we need to recognize that this formula, okay, with capital S in the denominator, gives you a random variable which follows a distribution that you know, a distribution that is a t distribution. Okay, and then we want to calculate the multiplier with S replacing sigma. And then we want to calculate a critical value t star so that the left tail probability of your t distribution is alpha over 2. And then you multiply t star with your multiplier s over square root of n to be your leg length, and then you use that in constructing your interval. You should be able to see the connection or the analogy between the two situations. Here we have a formula, we have a transformation, and here we have another transformation. The two transformations are different only at the denominator. Okay, sigma becomes s, and then the resulting distribution becomes different, but you still have them because they have PDF that is known by the software, so that with software you will be able to calculate them. You have a multiplier in this way, a multiplier in another way, but again, S replaces sigma. And then you want to calculate a critical value z, so following a z distribution. Here you use the t distribution, that's the only difference. And then all others are the same. So a few remarks. If your population is normal, then your sample size does not matter. We may use the t distribution anyway. However, if the population is not normal and the sample size is large, in this case, we cannot use the t distribution technically. Okay, if you go back to a few slides ago and look at that proposition, you know that if the population is normal, then you have blah 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 a t distribution. But if your population is not normal, then technically that formula really does not create a t distribution. But thanks to central limit theorem, your sample mean would be normal. Okay, the sample mean would be normal. It's just that the standard deviation of your sample mean would be unknown because you don't have sigma. So what will you do? You use this fact that when n is large enough, the t distribution would be very close to standard normal. So all we will do is to just use the t distribution as an approximation, and in some sense assuming that the big sample size can solve the problem with non-normality. Okay? So if your sample size is large enough, you will just ignore the distribution of your population and just go with your t distribution. Just go with the steps illustrated in the previous slide. If your population is non-normal and unfortunately your sample size is small, then we suggest you do not use t-distribution, because you just cannot say that formula produce something that is close to your t-distribution. Statisticians have shown a surprising thing in the case that when you have a non-normal population, when you have a small sample size, using the t-distribution, using the procedure illustrated in the previous slide, is wrong but not so wrong. The estimation is somewhat robust. Having non-normal population does not harm a lot. Okay? Technically, theoretically. But in practice, we suggest you don't do that. So as a summary to all the materials for today's lecture, we need to separate three factors. Whether you know the population variance, whether your sample size is large or small, and whether your population distribution is normal or not. When you have a known distribution, a known population variance, then as long as the population is normal or your sample size is large enough, you can use the Z distribution or the standard or the normal distribution. When your population variance is unknown, but your population is normal, you can use T distribution. Or if the size is large enough, sample size is large enough, technically you can use Z, and we will just use T as an approximation because that's the only way for you to overcome the fact that you don't have sigma. Okay, so these three cases here we use Z, the three cases here we use T. If your sample size is small and your population is not normal, basically in this course we have no way to deal with that. We need to rely on some non-parametric methods, but that's beyond the scope of this course. Not very difficult, but beyond the scope of this course. So when you have this situation, go to Wikipedia, go to find some technical statistic textbooks to find a way to deal with that. But you will see the principle will still be the same. It's just that the formula you need will be different. Okay, so that's the end of today's lecture. We want to do an estimation to the population mean. Eventually, we use sample mean as the center and open an interval. The lag length is the most critical thing to calculate. We do that based on a predetermined confidence interval, a confidence level. And the way to calculate the lag length depends on whether you know the sampling distribution of your X bar or a formula of your X bar. Once you have that, you use the Z distribution or the T distribution to do the calculation. That's the central heart of today's lecture. Thank you.